Greetings to you all. I'm Derek Korn, Executive Editor of Modern Machine Shop Magazine. Welcome to today's webinar that's sponsored by Quaker Chemical. Thanks for joining us. This webinar will examine the influence of cutting fluids on machining bimetal parts. The simultaneous machining of two dissimilar metals often causes issues with regard to surface finish, elevated cutting forces, machined part dimensions, and accelerated tool wear. Today, we're going to review the machining properties of bimetal parts, highlight methods useful for studying machinability and cutting fluid performance, and provide insight into features of cutting fluids that are best suited for such operations. Our presenter today from Quaker is Bob Evans, the company's Senior Research Scientist. Bob's presentation will be followed by a Q&A session. It's easy to submit questions to him, and I encourage you to do so during the presentation. You can simply type your question into the question pane on your screen, and we will do our best to get to all of them. So let's get started. Bob, please take it away.
All right, Eric, thank you very much for that introduction. And again, welcome to everyone for joining today's webinar. Again, we'll focus on the topic of bimetal machining. And we hope you find it very useful and interesting. To start, I'd like to first say a few words about the company I represent, Quaker Chemical Corporation. Quaker has been a major global supplier of processed fluids since 1918. So as you can see, we're quickly approaching our 100th year anniversary, which should be very exciting. We are headquartered in Conshohocken, Pennsylvania, and the picture shown on the slide actually is a frontal photograph of our headquarters located in Conshohocken, Pennsylvania. Quaker has approximately 4,500 global customers, including some of the world's largest manufacturers in the automotive and steel industries, with yearly sales of approximately $750 million. Quaker is a public company. It is traded on the New York Stock Exchange and is listed under the ticker symbol of KWR. This next slide shows the global presence that Quaker currently maintains. We have facilities in 27 countries, in 37 locations in 21 countries. And we have R&D facilities located around the globe. Our four main technical centers, however, are located in Conshohocken, Pennsylvania in the USA, right outside Amsterdam in the Netherlands, in Shanghai, China, and in Rio de Janeiro in Brazil. Within the metalworking industry, Quaker is a major supplier of metalworking fluids to the automotive, heavy equipment, and related industries to those sectors. To support our activities in metalworking, each of our global technical centers houses fully instrumented machining centers. And along the bottom of the slide, you can see some photographs of the machine tools that we utilize and have housed in our different technical centers. These machining centers that we operate and maintain are used for a lot of different functions to support the industry. This is from customer projects to customer service to supporting internal research and development, as well as conducting a more applied and fundamental research. A significant amount of this research that is committed within our facilities goes into supporting the emerging trends in the automotive engine manufacturing industry. So let's first talk a little bit about what these emerging trends are. Two of the major objectives right now in the automotive industry, which is driving a lot of the new development and the trends in manufacturing, are shown here on the next slide. One is the drive towards increased fuel efficiency, and the second is the drive towards reduced emissions. With these two objectives, a lot of the new developments in materials, processes, manufacturing procedures are resulting. And two of these results from these two industry objectives, one is the lightweighting of the engine and the lightweighting of associated components to the engine. And then secondly, related to reduced emissions and also related to lightweighting is the drive towards use of stronger materials, again, for engines, engine parts, and the component associated components. With the lightweighting being done to the engine and all the accessory components and the use of stronger materials has driven the design of new highly engineered materials and material combinations. Now, there has been much progress made in this regard that has achieved good advances in fuel efficiency, good advances in reduced emissions. So the steps that are being taken, the lightweighting, the use of stronger, harder materials for many very critical engine components is achieving very much of the target needed. However, it also presents some very increased and unique challenges with regard to fabrication of the part. And this is where Quaker and a number of other companies are spending a considerable amount of time looking at these machining challenges. What I have on this next slide is some examples of, in our work, where we are seeing some of the newer trends in engine production present some unique machining challenges. And when I mean unique machining challenges, I mean that whether it's the tooling, whether it's the actual machining conditions, whether it's the metalworking fluid and its capabilities, or a combination of these factors, there is a little bit of a loss of machinability, a little bit of loss of quality, a little bit of loss of production due to the changes. And again, I have some listed on this slide. The first one is the trend toward direct fuel injection. It has a significant positive impact on engine efficiency, and with that emissions. However, it presents some very clear and distinct machinability challenges, particularly in the injector bores and some of the unique configurations of the machining that are needed. A second one is the increasing use of hydroformed hollow camshafts. Again, main target is for lightweighting, which it effectively contributes to. However, it presents some unique machining challenges of these camshafts. A third example is the move towards higher wear and thermal resistant valves and valve seat materials. As you get higher combustion pressures, the stresses and heat in the cylinders are increasing, and it really drives the need for new materials to withstand these conditions, both of your valves and your valve seat materials in your valve train. The fourth one really relates to the whole area of boosting, engine boosting, and this is the turbochargers. We're seeing more use of some very high thermally stable materials like titanium and nickel-based materials being used in automotive applications, and a lot of this is coming from their use in some very critical parts of the turbochargers. The next example is the use of high-strength cast irons, and particularly two cast irons that are gaining more and more interest in use. One is the use of compacted graphitic iron for both engine blocks, for heads, and even as use as cylinder sleeves or liners in aluminum engine blocks. The second form of cast iron that's starting to see more use is Aus-tempered ductile iron. You'd see it more, not in the engine blocks or heads, but you see it in some support structures and gearing and so forth. So both of these forms of cast irons are extremely more difficult to machine relative to more conventional gray cast irons, or even for that matter for more conventional ductile cast irons. And last, you're seeing more multi-metal components being used, which is the topic of today's webinar. The use of bimetallic components, some background on them, some information on bimetallic machining, and some of Quaker's approach to looking at this area. What I'd like to do now is just to give a very quick definition of bimetal machining. And what we mean when we talk about bimetal machining, it's a condition or a process where you're simultaneously machining two dissimilar metals. And usually one of these metals is utilized because it serves to provide the lightweighting function to the part. And the second metal usually is incorporated because it serves to provide a role, fill a role where you need high strength, high thermal resistance, and quite often higher wear resistance. So in regard to engine production, there are, that we face in our work and that we see probably as two very significant challenges. There are two examples of bimetal machining that we've done quite a bit of study on within the engine production area. The first one is in the crank bore finishing or crank bore reaming operation. And what's shown in this picture is the crank bore as it's attached to the engine block. And here you can see the aluminum engine block, which provides lighter weight and obviously is used for that function. And actually, if you look at the picture, you can see the crank bore right here. You can see a second one right here. You can see a third one right here. And the picture is cut off. This may be, there may be a fourth or even an additional one after that. You can see three of the actual bores here. And the aluminum block actually makes up the bottom half of the crank bore. And then the top half is the main bearing cap, and this is typically a ferrous metal. It's either a cast iron, or more commonly used today, it's a sintered powder ferrous metal. And what this part provides, and the material that the part's made of provides, is the needed strength and rigidity for the high stresses that occur as the crankshaft is in operation. The second example that we see, or this bimetal operation that we deal with quite often, is the deck facing of the engine block. And again, here's a picture shown of the deck face of the engine block. And again, the lightweighting of the engine is obtained through the use of a cast aluminum alloy, and it's shown here, while high wear resistance and thermal resistance in the cylinder itself is achieved through the use of a cast iron cylinder sleeve. So when they face mill the deck face of the engine, they're going to face mill the aluminum and simultaneously face mill the ferrous component, which is the cast iron sleeve. So both of these examples present some increased challenges, increased difficulty in machinability relative to machining the aluminum by itself, or even the cast iron by itself for that matter. So I guess the next question that might be useful to discuss is why are bimetal parts difficult to machine? There are two primary factors responsible. One is the difficulty arises from the differences in the mechanical and thermal properties between the two metals used. And this is a significant factor, and we'll get more into this in a couple slides. The second factor is that, and it's related to the first in part, is that usually the machining conditions that are necessary to machine a bimetal part are a compromise between those that would be optimum for machining either of them. For example, an aluminum engine block and a cast iron cylinder sleeve, if you were going to machine aluminum by itself, you would use probably significant different machining conditions, significantly different tooling, maybe tool geometry, maybe even the metalworking fluid as well, than if you were going to machine cast iron. So again, there's usually a compromise met on the machining conditions, which would then decrease the productivity and the efficiency of the operation. So let's look first at the mechanical and thermal property differences between the materials. What's shown on this slide is a very general schematic of the crank bore. And what you can see is on the bottom, in the lighter yellow, is the engine block. And on the top is the main bearing cap, which is typically a ductile cast iron or a ferrous powdered metal. Again, the engine block is usually a high silicon containing cast aluminum alloy, such as a 356 or a 319, or in some cases even a higher silicon containing alloy like a 380. And right here is the bore that needs to be finished. If we look at the differences in the mechanical properties first, and what's shown here in this table are three properties of the metals that are involved in this part and subsequently involved in the machining. First is shown the properties of aluminum 356T6. And what is shown is the Young's modulus, the hardness, and the ultimate tensile strength of the material. And then, in contrast, are two ferrous materials that are used as the main bearing caps. The powdered metal, the 0208 powdered metal, and a 65 grade ductile iron. They're both very commonly used in the fabrication of the main bearing caps for the crankshaft. Starting off with the strength properties, what you can see going to the far right is the ultimate tensile strength of the aluminum is 260 megapascal. And the tensile strength of the two ferrous components are considerably higher, 503 and 448 megapascal ultimate tensile strength. And what this causes or results in this large difference in the strength, as these two parts are being bored or reamed simultaneously, you can have very rapid changes in the stresses and the resultant cutting forces that occur in a single operation. And these large differences in the cutting forces, even the friction properties, can give rise to some machining problems. If you look at the hardness, there's a big difference in hardness between the materials as well. The Rockwell hardness of the aluminum is 55 and considerably harder for the two ferrous components. And the same result, you can have some very challenges in machining because of the significant differences in the hardness materials of hardness of the surfaces. Probably what's more important, though, is the elastic properties of the materials. And you can see the Young's modulus, often referred to as the elastic modulus, that gives a measure of how easy it is to elastically deform under either a compressive or a tensile stress, the materials. And what you can see is that aluminum will start to deflect or elastically deform at a much lower pressure than will either of the two ferrous components. And this presents a situation that, again, under stress, whether it be a compressive or tensile stress during machining, that the aluminum could start to deform much quicker at a much greater rate than the mating component, either the powdered metal or the ductile iron. So all three of these mechanical properties present some unique challenges because of the differences between the aluminum and the ferrous component. If we look at the thermal properties, there's some differences that are equal in their concern and equal in the magnitude in the results they can bring about. If you look at the aluminum, and here shown it's just the ductile iron. If you look at the coefficient of thermal expansion, and what this parameter tells you is what is the dimensional change that occurs with increasing temperature of each of these materials. And again, what you can see that is the aluminum, as the aluminum heats up, it's going to expand considerably more than the ductile iron will. So as you're machining a bore that contains a ferrous metal, the ductile iron, and the aluminum, and you're starting to generate heat during the cutting process, during deformation, during friction, you're going to have the aluminum start to expand much greater and at a much greater rate than the corresponding ferrous component. And again, what this presents is some unevenness in the bore that's being machined, different flexure properties, some deflection that can occur, and ultimately in some very, very real machining challenges. To summarize these differences in mechanical and thermal properties, basically the large differences in the friction properties between the two metals that arise because of the differences in the mechanical and thermal properties can lead to very elevated machining vibrations and cutting forces, and ultimately have a negative impact on the real critical specifications of the crank bore during its machining, and that is the surface finish and the cylindricity that's produced. And we'll talk more about that a little later in the webinar. The second factor that contributes to the difficulty in machining, as I mentioned, is that typically there's a compromise in the tooling used and the machining conditions. I'd like to present at least two examples of this. And one is the tooling. Typically in machining aluminum, polycrystalline diamond or some form of synthetic diamond cutting tools is the best suited. You're going to get your best finish. You're going to be able to run at considerably higher cutting speeds, feed rates using PCD cutting tools. Unfortunately, they're not compatible with ferrous materials because of the degradation of the tool material, the diamond, as it solvates up into the ferrous component at higher temperatures. Typically, what you need to do is run with another material, and quite often in bimetal operations, carbide tooling is used. Carbides are okay for aluminum, and they're usable, but there is higher wear that results from the high silicon in the aluminum on the carbide, and it's okay for ferrous as well. So you can see that while there are optimum tool materials for each of the metals in a bimetal operation, you usually settle on a compromise. I'd like to show an example here of a study we did, and it kind of shows this effect a little bit. And this was a study to investigate the tool material effects in aluminum reaming operation. Now, this wasn't a bimetal operation. It was just simply aluminum. It shows the impact of going from a polycrystalline diamond tool to a tungsten carbide tool. Shown on the y-axis is the reamed hole finish resulting from the operation, and shown on the x-axis is the reamed finish at two different cutting speeds that we studied. Looking first at the diamond tool, and what you can see at the lower cutting speed, we got very good reamed hole finish down below 0.2 micron RA. And then as you go to a much higher cutting speed, it still maintained a very good reamed hole surface finish. Conversely, in going to a carbide cutting tool, you can see at the lower cutting speed, it's considerably higher, considerably rougher, and it's much more sensitive to increase in cutting speed. So again, it's not a bimetal operation, but it really highlights and demonstrates the impact of the tool materials and the differences between a PCD reamer and a tungsten carbide reamer. A second example is cutting speeds. Quite often with aluminum, like I mentioned, you're able to run at higher cutting speeds, and with iron, you need to go at lower cutting speed. So again, you're typically trying to reach a middle value that you can sustain acceptable quality for the aluminum and the iron. So now what I'd like to talk a little bit about is our studies in crank bore reaming. As a company that is committed to supporting the engine manufacturing industry and to be able to contribute support, to contribute suggestions, contribute and offer very high quality fluids for use in these processes, it is necessary to be able to study this process. Study it in our laboratories under controlled machining conditions. So we developed an in-house laboratory machining test with two criteria in mind. One is that whatever this test needs to effectively simulate the actual machining process. And then two, it really needs to replicate machining difficulties that are experienced during the reaming of the bimetal parts, particularly in simulating the crank bore reaming. So what we did is we've developed a workpiece that simulates the actual crankshaft bore, and this is shown in the picture on this slide. We fabricated it out of two materials, aluminum 356 P6, which actually simulates the engine block, the lower half of the bore, and then the top half is fabricated out of a sintered powder metal FC0208. This material is a very common powdered metal that's used for main bearing caps in the automotive production. It's primarily iron. It has 2% copper and a little under 1% carbon. And shown here is the microstructure, photograph of the microstructure of this material. And very characteristic of powdered steels, you can see the very distinct regions of ferritic material. You can see the high perlite, which gives much of the strength to the powdered metal. And then very characteristic of powdered metals, you can see a high level of porosity, which is the black region. And these areas of porosity also present some unique challenges in machining. And then the bottom piece, again, is a high silicon containing aluminum, cast aluminum, and the microstructural features of this material are shown. Again, very characteristic. You can see the copper-rich intermetallics. You can see the silicon plates characteristic of these high silicon containing alloys, as well as the iron-rich intermetallic pieces. To be able to demonstrate the difficulty in study bimetal machining, we also wanted to study and look at and test what is the machinability of a part that's not bimetallic. So for this, we also fabricated a part that was based on a bottom half of aluminum and a top part that was aluminum. And you can see this in the picture. Again, for this we used aluminum 356 for the bottom half of the bore, and the same metal, aluminum 356, for the top part of the crank bore. So here's a picture on this next slide of the fixturing of the part. This part has four bores that we machine in succession, and I'll just show you a very brief video of the actual reaming operation. The coolant is external. In this case, we're using a very standard semi-synthetic aluminum machining fluid. The rough bore is 15.5 millimeter in diameter. We're using a reamer of 15.9 millimeters, so we're increasing the depth of cut, or we're increasing the bore diameter by 0.31 millimeters. And which gives us a depth of cut of a little under 0.2 millimeters. And as you can see, we're using a feed rate down, and we're using the same controlled retraction feed coming out. Following reaming of the holes, the critical parameters we measure are twofold. One, we want to look at the reamed hole cylindricity, and two, we want to measure and look at the surface roughness of the reamed hole. And these are probably the two most critical parameters measured in the actual crank bore reaming operation: the cylindricity and surface roughness. What I'd like to do is spend just a couple slides here talking about why are these two parameters important, and why are they measured in industry, and why did we measure them in our study that we're presenting here today. First, with the cylindricity, again showing a schematic of the crank bore. Again, what you can see is the bottom aluminum engine block. The top is the ferrous component, the main bearing cap. Right around the edge here, you can see the journal bearings. the main journal bearings. You can see the journal of the crank, and then you can see the oil, which provides the lubrication. It is pretty well accepted and known that this process, the separation and lubrication of the journal from the bearings, operates under predominantly a hydrodynamic regime of lubrication. The oil that separates these two parts as the journal is rotating is formed as the lubricant is pressurized between the journal and the journal bearing, and it establishes a film of a certain thickness. The film thickness that is needed and reported in the literature to sustain a good separation in this operation is down at 2 micron thickness, and sometimes can even go down to 0.5 micron in lubricant film thickness. This thin a film is needed to maintain a good separation between the journal and the journal bearings. And really the thinness of this film really demonstrates how critical it is to have very good tolerances on your cylindricity. Because a loss of cylindricity of the actual reamed bore would subsequently result in a little bit of loss of cylindricity when the bearings are installed, and it could give rise to a very unstable condition of hydrodynamic lubrication, which could lead eventually to more accelerated wear of the bearings, and probably before that, a very noisy operation of your engine. If you look at the surface finish, another function and important property is the removal of heat from the bearings themselves. In this operation, there is heat generated, whether it's from the sliding action, from the flow of the fluid, from the stresses of the operation. Heat needs to be quickly dissipated into the surrounding materials. It needs to be dissipated up into the main bearing cap as well as down into the engine block. Surface finish can be a critical property in how effective this rate of heat transfer is. If the surface roughness of the reamed bore is too high, then it can have a potential negative effect on the rate of heat removal from the journal bearings up into the surrounding material. So along with the cylindricity, surface finish is equally critical. What I'd like to do is show the results that we got with that same semi-synthetic machining fluid when we conducted our crank bore reaming operation under laboratory conditions. And first I'm going to start with cylindricity. And just to preface that, the way we measured cylindricity is using a coordinate measuring machine. It has a hard body, and it'll measure the cylindricity of the bored hole. And here's the results that we obtained, and I'll just talk a little bit about this graph. What's shown on the y-axis is the cylindricity measured in microns. What's shown on the x-axis is the results of numerous holes reamed for both the aluminum part and also a bimetal part, again, which is an aluminum 356 and a powdered metal bearing cap. And for the aluminum part, you see the data points for 16 bores that were reamed. And what you can see is that they're all down below a cylindricity of 12 microns. Why this is important is, if you look in the literature, there are a lot of, you can see some different tolerance levels that people utilize. A real standard is 25 microns. Some are up at 35 microns. Some are even a little bit lower than 25 microns, sometimes down to 15 microns. So if you look at this tolerance level, you can see that if you would ream the aluminum part, you're safe and well below that tolerance level. If you go to the bimetal part, the aluminum powdered metal part, you can see of the 22 bores reamed, you can see that two results. One is that the cylindricity is notably degraded and worse than it is for the aluminum part. And actually, if we would consider a tolerance level up around 16 or 15 microns, you could actually see that some of the bores reamed might be approaching an unsuccessful level. So basically, what you see here is, as we would expect and as we saw, the reaming of the bimetal ore presents some considerable challenges and does give some poor quality. Regarding the surface finish, again, looking at the aluminum part, you can see that when we measured the aluminum surface finish, we get a very smooth surface quality, surface texture, surface profile. The reamed hole RA is down around it's under 0.3 microns in RA surface finish. And this is a very good smooth surface. And you can see the picture, a microphotograph of this surface down below the graph. If you go to the aluminum surface that was produced in the bimetal part, you can see the noticeable degradation of the surface finish, both in the RA that was measured up around 1.0 micron and visually in the photograph of the reamed surface. Here you can see notable scratches in the surface and in general a tendency towards just more of a rougher, abraded surface. Again, if you look at what most production facilities will set as a tolerance level for surface finish, it's typically up at about 1.2 to 1.3 micron RA. So if we set that tolerance level here in our testing, you could almost see how the bimetal part, the powdered metal aluminum surface finish, is quickly approaching that tolerance level. So our studies in this area have led to development of fluids. And again, our objectives are to study the process, understand the challenges, the subtleties of the process, to be able to simulate and investigate different elements of the process, and also to develop new fluids that can aid in improving the productivity, the machinability, and the overall performance in these bimetal operations. QUAKERCOOL 7450 has been developed within Quaker, and it is a semi-synthetic metalworking fluid, and it's designed for very effective machining of aluminum, but also very effective machining of bimetal parts and bimetal operations. And I'll just list a little bit of the logic behind the design of this fluid. One, it was designed to provide a high level of lubrication that is necessary to maintain constant friction and, more importantly, stable cutting forces that occur during the continuously changing conditions in a bimetal operation. I mentioned earlier that with the mechanical, the thermal properties, the expansivity of aluminum, the differences and so forth, that you can get some very regular or constantly changing friction and cutting forces. If you can elevate the lubrication properties of your metalworking fluid, you can minimize the impact of these changing forces and changing conditions. And that's what a main element of the design of QUAKERCOOL 7450 is. Second element is in these operations that have aluminum and a ferrous component, the cutting forces, the severity operation is going to be dominated by the cast iron or the powdered metal. The cutting forces necessary in a ferrous component is always going to be more significant than aluminum. So have a fluid that's very effective for bimetal operations, it has to be a good ferrous machining fluid as well. The key here, though, is there are many approaches to developing for ferrous machining that could potentially have a negative impact on its aluminum machining performance. This was an area that Quaker put a lot of effort into, and that basically is to engineer the fluid, maintain or to provide very good ferrous machining properties without any compromise to either the roughing performance or the finishing performance of the fluid on cast aluminum alloys. What I'd like to do is just show the impact this fluid can have relative to the standard semi-synthetic that we used earlier in both cylindricity and in surface finish obtained. And what this graph shows is the cylindricity. It's basically the same graph as we showed earlier. Cylindricity is listed on the y-axis. The aluminum part using the standard aluminum machining fluid performs well. The bi-metal part using the standard aluminum machining fluid shows the degradation in the cylindricity measured. And when we use QUAKERCOOL 7450 in this operation, we see a noticeable improvement in the cylindricity obtained with the cast aluminum powdered metal part. This is significant because it's a noticeable difference, and actually it gives cylindricity results that are very close and comparable to those that you would get with an aluminum part. And look at the surface finish, the same comparison. Here we have a graph showing the aluminum surface finish after reaming. It shows the bore finish tolerance right up at 1.2, and on the y-axis is the RA of the ream surface measured in microns, and on the y-axis first is the ream finish with an aluminum part. And here you can see that both of the fluids, the standard aluminum machining fluid that we used and the newer developed fluid, QUAKERCOOL 7450, both are highly effective in giving good finish on the aluminum part. And that wasn't surprising, and that was expected. The interesting result was, as we showed before, that the standard fluid on the bimetal part resulted in a very noticeable degradation of the surface finish. Again, up at 1. Newer developed fluid, QUAKERCOOL 7450, shows a marked improvement in the surface finish, the ream surface, obtained when the reaming of the bimetal part was conducted. Granted, there was a slight degradation, a slight increase from about 0.28 up to about 0.442. Nevertheless, both of these surface finishes are very good. And just to show the finishes obtained, again, earlier we saw the finish of the bimetal part using the standard fluid. We noted the general graded roughness and the scratches that can be observed. And then if you look at the ream finish utilizing QUAKERCOOL 7450, you can see a very good quality surface, minimal light scratching, but overall a very smooth and consistent profile on the surface. So a little bit more about QUAKERCOOL 7450 in general. Again, it is an aluminum and a bimetal machining fluid with a good bit of field experience so far. It is a fluid that's being globally utilized by many automotive OEMs, by many Tier 1 and Tier 2 manufacturers to the automotive industry. It's being used in the machining of aluminum engine blocks, cylinder heads, and various associated components, such components being valve seats, valve guides, steering components, as well as direct fuel injector bores. Some of the behavioral features of this fluid, it's a very clean operating fluid. It is a semi-synthetic fluid, very tight emulsion, wets out well and leaves the machine very clean during operation. It's good tramp oil rejecting properties. It's very compatible with increasing water hardness, giving very consistent performance and stability over a relatively wide range of water hardnesses in the emulsion. Being a tighter emulsion and stable to some of the influences of contamination and changes. It provides a very good sump life in its operation with low consumption. And regarding its microbiological properties, it is and has been found to be microbacterial resistant and resistant to as well to other forms of gram-negative bacteria as well as fungal resistance. So I'd like to present two conclusions to the webinar and some of the messages to remember and take away. One is that bimetal machining, again, is becoming more used, more prevalent in industry. And as the demands for continued lightweighting and at the same time keep power to the engine, which means higher combustion pressures, higher stresses to the part, there's going to be more use of multi-metal or bimetallic parts as we go forward. And as we know from the operations, and have you seen a little bit today in this webinar, bimetal machining certainly presents significant challenges with regard to the machining that's done, the metalworking fluid that's used, tooling that's used, the machining conditions that's used. And we feel we have a good start to our understanding. Definitely there's more progress that we plan on making in this area. Secondly is QUAKERCOOL 7450, as we just finished discussing and presenting in part. It's a new fluid designed that gives us very good effective performance in aluminum operations, and more relevant to this webinar, it gives very good performance in bimetal operations, particularly where you're coupled a cast aluminum part with a harder ferrous component. Before I finish, I'd like to make an acknowledgement to some of this work. For this study that was presented in this webinar, we collaborated with the Pennsylvania State University. We collaborated with their departments of Industrial and Manufacturing Engineering and their departments of Material Science and Engineering. And the collaboration was very effective, very fruitful, and I would just like to acknowledge the research team at the university for their efforts in the study that was presented. And with that, I'd like to conclude by thanking everyone again for joining this webinar. Again, I hope you found it informative and interesting and hopefully useful. So again, thank you very much. And with that, now we'll accept any questions that you may have on any parts of the webinar presentation or any other thoughts or questions that you might have. Thank you again.
Thank you, Bob. I appreciate that presentation. Before we transition to the Q&A, though, I do want to remind everyone that the webinar is being recorded, and you will receive a follow-up email with a link to it, so you can revisit this whenever you like. While we've already received some good questions from the audience, there's still time for you to submit one via the question pane. First question here. Would using MQL or minimum quantity lubrication be recommended for this type of bimetal machining?
Oh. All right, Derek, thank you for relaying that question. I'll give my thoughts on that. I think MQL may have some shortcomings in these kind of operations. One is that it's very important to maintain the aluminum at a relatively low temperature. And MQL, while it's very effective at reducing the frictional heat that can form in these operations, a water-based fluid and a flood application is very effective for cooling the part. And as we talked about, and showed before, the effects of heat generation on expansion of the aluminum components can be very critical. And if you're machining just aluminum and dimension changes because of heat, it may not even be as critical as if you're machining both a ferrous component and aluminum and you're not able to cool the parts as effectively. So for this reason, while MQL certainly may have a place, may be able to be used under certain circumstances, it's probably by far not optimum an application process for many of these bimetal operations, particularly the two that I mentioned today, and certainly the one that I focused on, which is the crank bore reaming.
Okay, another question here. Are the mix ratios the same for 7450 regarding the type of material that's being machined? What our experience has showed is that if you determine concentration that suits your operation for the aluminum machining that's done in the operation, that same mix ratio or concentration of the QUAKERCOOL 7450 will be effective for the bimetal machining. So if you're doing block machining and you're finding that you're doing your bolt holes, your roughing, your tapping, if you're doing any finishing operation, whatever concentration you're using for those operations will be very well suited for that facing operation where you're going to go over the aluminum as well as the ferrous component of the cylinder sleeve. So to summarize my answer, basically it's the same mix ratio or concentration. Okay, yeah, you mentioned a few operations there. Another question here, will this product work well in deep hole reaming or drilling?
Yeah, it will. It is being used in industry for some deeper hole operations, and in our laboratory, we've tested some deep hole operations up to 6, 8 hole depth times tool diameter, and given the with the certain and the optimum machining conditions and tooling and so forth, it is a fluid that is very well suited and effective for deep hole operation, both on aluminum and ferrous materials.
Another question here. Have you seen product performance advantages with 7450 in operations that run aluminum alloys only?
Yeah, this is a good question. As I mentioned, QUAKERCOOL 7450 is a very effective aluminum machining fluid, as well as providing utility on bimetals. I have to say that there are a number of very good aluminum machining fluids that are used in industry that can provide effective performance in aluminum machining. From our experience, both in its use in industrial operations and in our studies within our laboratories, if I had to say one attribute, one benefit this fluid brings is in some very critical finishing operations. If you're doing some padded reaming operations that are very critical, very sensitive to scratching and entrayment of particulates that can bring some problematic issues to the surface finish. If you're doing some injector bore finishing that have some very unique geometries, chamfer, you're finishing anything with an angled or chamfer surface, what we found is that QUAKERCOOL 7450 tends to provide some unique advantages and benefits. So if you're doing tapping, if you're doing roughing, if you're doing some standard reaming, there are a lot of fluids that provide good performance. The real utility of this fluid is in some of these more challenging aluminum operations, again, like padded reaming and some unique geometry holes like DI bore, direct injector bore.
Another question here, I guess this is regarding your testing capabilities. Do you measure friction, vibration, or heat dissipation during machining process?
Derek, thanks. Yeah, we do. Actually, in the testing, I presented cylindricity and I presented surface finish. But we also measure cutting forces, and we measure machining vibration on our machine tool that are used for these studies. What we can measure, we use a dynamometer mounted on our spindle, and we measure thrust forces and cutting forces. And if you know the rake angle, your tool, then you can calculate your frictional force, your normal forces, and not only can you get the frictional forces, you can actually then derive your coefficient of friction. So we can measure friction, and we can actually derive our coefficient of friction in the operation. And with we have an acoustic emission sensor that we utilize. So in all of these operations, we also measure machining vibration. And it's really a mechanism more than a result. And what we have found as a piece of information is that the machining vibrations that occur during this operation are probably the most critical performance metric we measure that will then indicate how good is the cylindricity and how good is the surface finish. So to answer the question again, we measure both friction and we measure vibrations.
Okay, I have a fairly specific question here. Is this QUAKERCOOL fluid recommended for 303 stainless and 6061 aluminum bimetal side cutting machining?
Well, it would be a very, you say 6061?
Yes, that's what they have here.
6061. It will give good performance on 6061 P6. We have investigated it on stainless steel, and I believe it is being used on stainless steel, or we have it in operations in stainless steel. So we know it has good performance on both of those materials. Yeah, it is being used on 300, the austenitic stainless steels, as well as some 400 grade stainless steels. How it would perform in a multi-metal operation that utilizes the 6061 with the stainless, it only have to give my opinion, and that is I think it would do pretty well. But I can't say for sure because we don't have experience with it in a bimetal operation using the 6061 and the stainless, and we'd have to look at that. But my opinion is that it would probably give you a fairly good level of performance.
Okay, we're at the top of the hour now. We have time for one more question here. Kind of segueing here, are tool manufacturers studying other composites for this type of bimetal machining process?
Yeah, they are, Derek. And mention carbide, because carbide is a very common tool material that are used. But there's a lot of development in tooling that's being used, starting to be used, and is ongoing. There's developments in new types and grades of polycrystalline diamond that is reported more compatible with the ferrous powdered metal. So we may start to see increased use of PCD even with these ferrous components. There's a lot of use of polycrystalline or cubic core nitride based tooling that is being used for these bimetal operations. And definitely there's been a lot of effort and continued effort in coatings. Titanium-based coatings and other ceramic-type coatings, they're being laid and deposited onto carbide to give it improved performance. So there's a lot of different approaches to tooling and tool materials that have been made and are continuing to be looked at.
All right, good deal. Well, that's all the time we have for this webinar. We certainly hope you found it helpful. If you have any other questions or if you're viewing a recorded version of this, Feel free to email your question directly to Bob at the email address that's currently on the screen, and he will get back to you as soon as he can. So on behalf of Modern Machine Shop and Quaker Chemical, thanks for joining us, and enjoy the rest of your day.